So based on a very rough analysis done on the board with hand sketching, we conjectured a power function with power negative 0.64, perhaps negative 2/3. And then with the information, assuming this information comes from the graph of the curve, y is 52 cycles per minute when x is 32 centimeters. We obtain this model for frequency versus length and a graph that looks something like this. Okay, now that was, I'm not going to say I know how this ought to work out, but I'm not saying whether it works out close to this or not. Okay, I'm not saying whether 52 cycles per minute is associated with a 32 centimeter pendulum. What we want to do is move on to a capstone activity where you actually verify all this stuff and do it for yourself using your own data. So what we want you to do is first of all make your own pendulum. Now you want to find something to hang from a thin thread, something like this. A washer would be great, a ring would be great, as long as the center of mass of this thing is in the middle. Okay, we don't want a big stone down here or up here. If there's a big stone, it's okay if it's here on the side at the same level as the middle. And we measure the length of the pendulum again from the center to the point where we're holding it with our fingernails. And then using whatever measure you choose to use, we're going to observe counts for several different lengths. Now that means we have to measure the length, and that's where you could measure it in centimeters, you can measure it in inches, you could write it in feet, whatever. Okay, but we're going to observe counts for several different lengths. By several, I mean you should have at least 7 or 8 different lengths, and no two lengths all that close together. Okay, because you want a nice spread in your data. Okay, so make your own pendulum, observe counts for several different lengths. Then what are you going to do? You're going to graph the frequency versus length. And you use an actual scale here. You'll have a scale for each axis. The reason you'll have a scale now is you do have measurements of your length and you do have numbers for your frequency. So you're going to need a scale for your graph in order to sketch the points. Okay? Now, having used that scale to sketch your points, you're going to ignore your scale and you're going to do just what we've done. You're going to do this geometrically. You're going to ignore your scale. You're going to sketch your trend curve. Now, when you sketch your trend curve, you don't try to go through your data points. You sketch the curve. You know, your data points are here, 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 here. And you don't try to wobble up and down and up and down and up and down to hit every data point. As a matter of fact, when you do real-world data, it's actually mathematically impossible that your curve will actually go through any of your data points. Now, when you're sketching them on a piece of paper, you know, the line you're using to sketch has a certain thickness, and that line might just completely obliterate some of your data points, but there is no mathematical reason to expect that the actual center of the actual trend line actually goes through the center of any point. Now, the center of a point has no dimension, and the line has no thickness. So I'm stretching the language a little bit. Okay, so anyhow, ignore your scale, sketch your trend curve, following the trend that you think your data actually indicates. Don't try to hit any data point. Don't go from your first data point to your last data point. Don't go through this data point here because you think it's a pretty point or because you think it has some special meaning. All your data points have the same meaning. You're trying to get as close on the average as possible to your points with a smooth curve. And actually, you might know this, but at this point, it's kind of unlikely. You're trying to minimize the squared deviations of your data points from your curve. But when you're doing curves, that even gets abused a little bit. Not abused, but confused. Okay, so You ignore your data points, sketch your trend curve. Ignore your data points now, and now everything you do, you're going to use your curve to estimate everything. Your data points are done. You've done your trend line, you've got your trend curve, and that's what you're going to use. Your data has given you that curve, and again, you're done with your data. So for example, you would not use 52 cycles per minute and 32 centimeters if this was a data point, okay, because unless your honest trend line actually happens to go through that data point, but there would be no reason to actually choose that particular point. You would choose a point on your curve to get your X and your Y values that isn't a data point. Point on the curve that is not the data point, okay? So you're going to ignore your data points, use your curve to estimate now the Y factor. And that's simply, again, when you double X, what factor does your Y change? Is it 0.64? Is it something else? 0.7, 0.6? Could be. I'm not going to tell you. I know what it should be. I don't know what it actually will be with real-world data. But it's going to be pretty close to what it should be. Then you're going to find your power P, log of your Y factor divided by log of 2. And you're going to write your Y equals AX to the P model. Or if you prefer, your F equals AL to the P model. So, you'll know the factor, the power P, at least as your data seems to indicate it. Then you're going to pick a point on the curve and find its X and Y coordinates. Now this is what I was talking about before. You're not going to pick a data point. If 32 centimeters, 52 cycles per minute is a data point, that's not the point on the curve you want. You pick a point on the curve that's not a data point. And usually something closer to the center of the curve than to the ends, but there are judgments you need to make when you do that, and you can think about that. Okay, not going to expect miracles in the choice of which point to use. Pick a point that you think is a solid point on the curve, find its X and Y coordinates, substitute those coordinates into this form, and solve for A. You're going to have P already. You're going to then have a Y and an X. You're going to be able to solve for A, just as we did over here. No mystery to the solution of that equation. Having solved for A, then you write your model. Now, what did we do here? We solved for A. We got 480. Okay, our model was AL to the negative 0.64, but now we know A to be 480, so it's F equals 480 L to the negative 0.64. Even if you measure in centimeters and cycles per minute, you're not likely to get 480. You're not likely to get 0.64 either. It's just statistically unlikely. There's too much variation in the data, so don't even try to get these numbers. I suggest you might want to measure in inches, so you're not even confused by these numbers. You're going to get different numbers. Okay, then the last thing, and I'll give you some hints here in a minute, but in another video. For each measured length L, use the model to find F. Okay, that means you got a model of Y versus X, or F versus L. X really is now your length L, Y is your frequency F. So you might write it like this. For every length L that you observed. So for example, if you observed 32 centimeters, you plug 32 centimeters in here and see what you get for F. Okay, if you observed a length of 20 centimeters, you would plug 20 centimeters in and you would get a frequency F. Now, if you're doing this in inches, okay, maybe one of your pendulums is 14 inches. You plug 14 inches in and see what F is. And you compare that with the observation you made. Remember your observation, you can't observe this thing down to the nearest hundredth or even the nearest tenth of a cycle per second. So there's going to be some discrepancy. Okay, you didn't get exact information when you observed your data. So let's see what you get. So you plug in the L, you get F, and you compare with the F you got from the observations. Use your model, your function, to predict F, and compare with the F that you got for that length. Okay, so I'll say a little bit more about this in a subsequent video, but right there is a capstone project that will hopefully bring all this together in a way that gives you a real tool to be used later on.